Okay, and welcome to Chapter 7, Ocean Circulation in the Oceanography course. This chapter is a compilation, or at least sort of a synthesis from the last two chapters where we talked about the properties of seawater, and then in the last chapter, in Chapter 6, we discussed the interactions that occur between the atmosphere, between air, between wind, and ocean currents, and how the spinning of the Earth factors into all of that. You remember the Coriolis effect, of course, that we talked about in the last chapter. So what we're going to be talking about in Chapter 7 now is how that all sort of fits together in this huge global pattern of ocean circulation. And not only, in terms of the physics of it, but what that means for living organisms, because that's the intent, of course, throughout the entire course, is to relate the ocean and its environment and the kind of species and where they're found, because that's so important, because differences in environment drive for different types of organisms that are found there. Now, we'll get more into that later on, but back to ocean circulation, I think it's interesting. This map is a map that was drawn, I want to say Ben Franklin did it, but I don't think he did, although I know that he was aware of this and I think wrote about it, but I'm not sure if he did this. But a map drawn during his time where they've clearly illustrated this, basically what we call a river of water moving through the ocean, right? That area that's in the darker colors there where you see all the ships. That's what we all, of course, know is the Gulf Stream. And that moves around the Atlantic Ocean basin. In the upper left, you see there's a smaller little map in this circular fashion, just like we learned in the last chapter, because of the Coriolis effect that it spins in this direction. And this was very important to the Europeans and folks traveling between these two continents, especially back during this time, because, sailing ships were basically at the mercy of the winds and the currents. So these faster moving rivers of water amongst the ocean were a faster way to get those ships back and forth. And if you look at the old charts back during this time, you sailed to Europe from the Americas across the northern part, and then you came back along the southern part. And as a matter of fact, that's kind of where Columbus's ships drifted, as they drifted into, of course, they ended up, maybe a little bit further south than that. But this Gulf Stream has been known, if for no other reason, even if it's not science, of course, that's what drives a lot of things, is the science to understand it for the business. This is important for trading ships moving back and forth across the Atlantic, as well as for the explorers that were coming over, right? So we've known about ocean currents and what they do for quite a while, but now we know a little bit more about why they do what they do. So first, let's talk about the types of ocean currents, right? They're the ones that are on the surface, and then the ones that are much deeper. And we'll talk mostly about the ones on the surface because those are the ones we mostly interact with. And again, the deep, out in the middle of the ocean, the productivity there isn't really all that fantastic. There's not a lot of producers, things that photosynthesize. There's not a lot of food out there. I don't know, people have this misnomer sometimes, like the middle of the ocean, is full of all kinds of critters. It's really off near the coastlines and in shallower, relatively shallow water where we find most. So it doesn't mean there's not critters out there. But so, surface currents are the ones that we're going to be more concerned about in terms of how it affects us. And obviously, from an interest point of view, from a biological point of view, how it affects the organisms there. Now, the surface currents are going to be those ones above, and that's actually spelled wrong, I just noticed. Supposed to have a C between the Y and the N, but remember, this is the pycnocline. This is the change in density. Remember, this is the part from the last chapter where, you go through this change in density rather rapidly. It's about at 1,000 meters or so. So these surface currents are going to be the ones that are going to be up in that area, up in that area above the pycnocline, actually kind of above the thermocline. That first, 100, 200 meters, I said 1,000 meters, but that would be kind of the end of the cline above that. The stuff that's driven by the wind. Your wind doesn't drive the really deep currents. There's something that drives them. We'll talk about that. But the wind blowing over the water causes friction and pushes it. It's not very efficient, though. That's why, you need some pretty good sized wind to get some decent waves, because 98% of the energy in the wind, only about 2% actually gets transferred to the water. In other words, only about 2% of the energy of the wind pushing against the water actually causes the water to move, okay? Friction and all those kinds of things and physics and all that. Well, this is a horizontal movement, right? And so this whole idea of the wind moving the waves is important, but it only affects about 10% of the ocean water. And what I mean by that is not horizontally, but again, depth-wise. The surface part above the cline, whatever one, pick your cline there, pycnocline, thermocline, even halocline, it only makes up a very small portion of the ocean water. So the effects of surface currents is only going to affect, a very small part of the ocean water. The continents have an effect, right? They kind of turn the ocean water currents into basins, if you will. Sort of like if you think about the water going down a toilet, right? Now, I think I talked about in the Coriolis effect, it doesn't change in the southern hemisphere the way the water goes down the toilet. The Coriolis effect affects water in a much grander scale, okay? But in the northern hemisphere, again, to reiterate, if you look at the map down below, it's a little easier. The waves are going to move in a clockwise direction, and in the southern hemisphere, they're going to move counterclockwise. So they're going to spin to the right in the northern hemisphere and spin to the left in the southern hemisphere, right? So the Gulf Stream picture, right, follows exactly that arrow that you see there. What you're looking at up above in that other chart, the colorful one up there, is actually the speed of the currents. Actually, what you're looking at, this is really neat. The ocean dynamic topography, the scale that got down there, because of the way that the wind blows over the ocean, it causes the ocean to have ripples, right? Like if you were blowing over hot coffee, same thing, but in this really huge scale. And in some degrees, the differences can be pretty big, 120 centimeters, 80 centimeters. That's a good distance, but over the expanse of the ocean, right, you would notice that. But the per second part is because these waves are moving through the ocean. So it's really kind of neat to think about the ocean, even if it's flat, right? You got flat calm. It's still this, this kind of like in a much smaller scale. It's like the layer of the tub, So the currents are going to influence how that moves around. The temperature, all this kind of stuff is going to have this really grand effect on what it does to the ocean. And that's going to have a really big effect on what it does to the planet. Not just where predators live, but why the planet is the way it is. Why, again, why deserts are the way they are, and why conditions in the ocean are the way they are, right? All right, how do we measure surface currents? Well, there's a really easy way, and I actually did this in the Keys when I had a job. After I got out of grad school, I got hired for a summer looking at coral reef in the Keys. It was great. All I did was basically scuba dive all day long, examining reefs. But one of the not so glamorous jobs we had was measuring the currents moving across the different reefs down in the Keys. Reefs. So we would take our boat and we would go out and we would throw something overside, a floating device. Kind of, I don't remember exactly. It seems to me ours was orange, but it was similar to this thing that you see in the picture, but it didn't have the little Duma flashes on it. It didn't have an antenna. It just basically was something that floated. So he would throw it over, and then we sat on the boat and let it float as the tide went in and out, right, which is a current again. And every half hour or so, we would use a compass and a map. Well before GPS and phones, folks, we would shoot our position on a chart. And we were charting the speed and the direction of the surface. So it was basically, and it wasn't such a glamorous job because what you did is spent all day out in the hot summer sun in the Keys floating in a boat. And that's cool for a while, but after a while you're pretty, we had a bimini top with a little bit of shade, but it got a little bit old. But nonetheless, it was interesting, of course, as we tracked the currents moving out in and out. Now, there's ways now that are a lot less cumbersome, right? We got the ability to have these antennas on that little device, which is just floating. So that could be in real time, could be through a Bluetooth on your phone now. My gosh. You could be tracking that thing floating in and out as it's moving in and out. You could track it as it's moving through those big currents of water in the ocean, not just the tides, right? And you could have that relayed through satellites. Indirect methods involve things like satellites using not the ability or to transfer the information from something floating, but actually to read the currents themselves. And they do it real kind of cool. Radar altimeters telling the heights again. So a satellite flowing over looks down on the ocean, and it can actually see the currents by looking at the height of the water. And if you think, as water's being pushed along, it bunches up a little bit, doesn't it? That's, again, why the ripples on the top of your coffee end up the way they are, right? Doppler meters, those are neat. So you get water flowing by something, and you have you measure the Doppler effect. The Doppler effect is why a siren on an engine, and I'm not even going to try to recreate it because it'll sound awful, but a fire engine, whatever, the sound, it increases in pitch as it's coming towards you and decreases in pitch as it goes away. It almost sounds like they turned it down in pitch, not in volume, right? Not in volume. That's the Doppler effect. As it's coming towards you, the sound waves are being compressed against you because the fire engine's coming at you very quickly. And so that's causing the pitch to go up, and then when it's going away so that it's stretching out. It indicates there are waves of sound, right? Well, there are waves of sound and waves in the ocean, so they can measure that. It's the same way you get busted with a radar gun from a cop. He's using radar. He's bouncing a signal off you and measuring how long it takes for it to come back. That tells you how fast you're going. Probably have something different now than that, right? All right, so that's how you can measure it. We can also do it very hands-off with this thing called Argo. These are free drifting profiling floats, like the little thing you see in the picture. So these research ships drop them in the water, and they just float. They're cheap. They're inexpensive. They gather, relatively speaking, they're cheap and inexpensive. They gather profiling, salinity, temperature, ocean current, wind speed, precipitation. They can measure all kinds, all uploadable, right? They can also profile at different depths too. For example, they can descend down to a particular depth, and they can read all that information. They can drift at that depth for, a week and a half, and they come up to the top and transmit that data, right? Isn't that neat? And as of September of 2012, there's over 3,500 of these floats floating around the ocean. And they signal back, of course, when the batteries are low, and they they go out and are picked up if they're damaged. I guess if you lose a signal on one. I mean, I don't think they could make something. It'd be cool if they could make something like this biodegradable, so it lasted for a year, and then we didn't have to worry about picking them up. But I don't know if that's the case. But this is kind of neat, right? So we can get real. That's why you can get on the internet now, and you can see, what are the waves like out in the middle of the ocean? It's one of these gizmos that's giving that information to you, if it's available. A lot of times you can get that information from buoys and things further inshore, but I don't know if you can do real-time Argo. Somebody can. That's neat, right? Okay, gyres and currents. Currents are rivers of water. Gyres are spinning things of water. If you think about, again, the water spinning down your toilet, right? So currents occur equatorially, anyway, along the equator. And my kids are always getting this backwards, and I always remind them, when you look at the equator on Earth, no matter where you are, think about the wind is blowing to the west. So don't worry about the wind or Earth spinning. The winds blow along the equator in a parallel. They blow along either side of the equator, but they blow to the west. So when they blow to the west, so if you think about this, and my pen is not working, so okay, hold on, I got to use my finger. There's the Earth. So the winds are blowing to the west in parallel fashion across the equator, and that's driving, that's a result of the Coriolis effect. So they're spinning in the northern hemisphere clockwise and the southern hemisphere the other way. So if you get confused with the Coriolis effect, just remember the winds and the currents move along the equator to the west. All right, to the west. So those are the equatorial. There are equatorial counter currents too. Water blows to the or water moves to the west, and it's cycled back through a counter current. Not necessarily a deep water current. There are some really, really deep water currents, but deeper, of course, more pronounced in the Pacific because it's much bigger, right? The Pacific is a lot bigger, so the Coriolis effect is a lot more pronounced. Water's got to blow over a long distance before you get the Coriolis effect. That's why it's a myth that your toilet flushes the other way in the southern hemisphere. I remember in the Navy when my ship went across the equator, how many guys ran down? No, it's the same. I'm like, yes, it's only a toilet. Anyway, also water blowing to the west across the equator and the Pacific being bigger again, water actually builds up a dome. Isn't that amazing? On the western side. If you look at it across the ocean in some significant or horizontal difference, I don't know what it is. I think I have some data on that. But anyway, you get this water building up, like, again, you blowing your coffee across the cup. It gets a little higher on the other side. So these waters moving, it has to do with the El Nino, by the way. We'll talk about that later on, all right? So you got the Coriolis effect moving the water, and everything's moving westerly. And, of course, a lot of this equatorial countercurrent is basically moving the water the other way. So a stronger Coriolis, a stronger wind moving it west means a stronger countercurrent coming the other way. Now, western and eastern boundaries have to do with continents, all right? Western boundary is not the continent's western boundary. It's what the current hits on the west side, okay? So, for example, the Gulf Stream, right? The Gulf Stream, its western boundary is going to be where it hits us on the east coast. Now, think in terms of the ocean basin. That's all you got to do. The west side of the Atlantic is, Florida and United States and all that sort of stuff. Now, again, along the western side, and remember that that water blows along the equator. So if you think of water blows to the west across the equator, so imagine the ocean in your head again. I wish I could draw this, but I'm not a very good artist anyway. So the water's moving west across the equator. It hits the western boundary. It hits a continent there. It reaches its western boundary, and it's even follow my fingers. I don't know if the video shows up on the recordings. I hope it does. But anyway, so we're moving along the west, and then it hits the boundaries, and it gets deflected. Gets deflected in the Coriolis direction. So think about the water's fanning out that way, fanning out this way. I am going to draw this because I don't know if this shows up when the recording, but the water's flowing. Here we go. Water's flowing this way and then being deflected up in the northern hemisphere, blowing this way, being deflected up or down in the southern hemisphere. There's the continent of North America there. There's South America there. The equator's in the middle. The wind's blowing to the west, right? Makes sense? So the warm water is always going to be on the western boundary. That's why Florida has got warm water and California doesn't. I lived out there. You go in the water in California, even in the summer, it ain't much above 70. There are not a lot of people splashing around like they do, especially in Siesta Key, or at the beaches here in Florida. The eastern boundary, so our west coast, San Francisco, the other side, right, is going to be cool water. For the opposite reason, follow that current all the way around, and I got a map that'll show you if you can't visualize that. And don't feel bad. I'm not very good at visualizing this stuff. That's why I have to sometimes stand back and think about it. And then there's a boundary, right? There's an easterly water flow where the wind shifts from the east to the west in those mid latitudes, and that's gonna change things. So that's gonna be currents. Gyres are gonna be big loops. They can occur subtropically. Where's the subtropics? Florida. We're in the subtropics. Central Florida. We're not tropical. That would be, the tropics in southern Florida. We're not temperate. Temperate would be more seasonal, spring, summer, winter, and fall. And more than just a couple of days of those like we have down here, right? So the mid-latitudes, and then there are some spinning gyres of water in the subpolar regions, which actually move opposite of the subtropical gyres, like gears moving together. If two gyres come together, two spinning things come together, they're going to turn opposite of one another. Think about gears, right? Winds move from the east in the polar latitudes. And again, I got some charts that might help you understand this a little bit more clearly as we move through this. So, all right, so those are some of the terms. So here's the big picture. We're looking at the ocean. There they are, the red arrows right along the equator. Find the equator. The red arrows you notice in both ocean basins, it's a little easier to visualize in the Pacific, move from the right-hand side of the map, right? They blow to the west. That's what we mean by westerly wind. They come to the west. Let's go with the Pacific, northern Pacific, right? Northern equatorial current, that's what that is saying there, hits its western boundary, Japan, Philippines, spins to the right because of the Coriolis effect. It's being deflected, bam, and bam, smashes into to Asia, and it spins up to the right. The blue water, those are the cold currents. So the Shio up there in the upper right is probably in response to the Kuroshito, which is moving water up that way. So that's some of the water that flows back. Think again about the oceans being a big old basin, like a tub. There is another subpolar gyre, the Alaskan. Notice how it's spinning opposite of the North Pacific, right? Two gears coming together. Look at the arrows coming together. Now, here's the cold part. As the water moves across the North Pacific current, guess what? It cools off, doesn't it? It's near the poles. So when the California current keeps turning to the right, because now it's hit its eastern boundary, it's cold. And even in the summertime, like I said, it's cold. But look at us on the other side. Isn't that nice? The water comes from the North equatorial current in the Atlantic Ocean, hits the Caribbean, and gyres around through the Gulf Stream. We'll look at that later on, and moves to the right, bringing warm water up to Florida. Keeping our oceans nice and warm, right? And also there are some other effects, but we'll get to that in just a second. See how that all works? It's all opposite in the southern hemisphere. So in the southern hemisphere, if you're going to Australia, or you're going to the southern Pacific Ocean, if you're going to the southern Pacific Ocean for nice warm water, you're going to be wanting to go over near Australia to the New Zealand, Guadalcanal, Borneo, those areas, right? If you want cold water, you're going to be going over there to the western coast of South America. Likewise, if you want to go to a nice warm beach, you're going to go to a Brazilian beach because it's going to be warm, whereas the beaches in Africa are going to be cooler in the southern hemisphere. Okay? All right. Now, the cycle times are very slow in the north. For example, the Northern Pacific Subtropical Gyre, which is really that huge spinning of water. It's a big gyre. Gyres can be big or little, takes about 6 years. The Northern Atlantic Subtropical Gyre is a little faster, all right, smaller basin, only takes about 3 years. And if you look at that Northern Atlantic Subtropical Gyre is the path those guys were charting on the map, right? So that big gyre is the spinning of the Gulf Stream moving around the Atlantic that helped these guys move back and forth. As a matter of fact, like when the Europeans used to leave Europe to go further, when they tried to figure out what was in South America and beyond that, they would go down this way following the current. Then they would make their way across the equator. It was kind of slow sometimes. It used to take them a while. But if they get across, they get down here and actually get pushed along by these winds. And then it became a little treacherous here, and it was really kind of hard moving across because when you get up into the equator, there's hardly any wind at all. It's called the doldrums. All right, so now let's look at what happens to the water, because this is going to have a big effect, but a more localized. So in other words, not just the spinning of the water around the basins, but kind of what is going on in maybe not localized, maybe regional. Maybe we call this the intermediate effect. This is something called the Ekman transport. The Ekman transport is named after a oh gosh, what I talk about it later. Swedish, I think a Swedish physicist or something like that. And he basically is the one to figure out why the water's moving this way. And I'm trying to remember why I put Fridtjof Nansen's Fram. He was a oceanographer, the guy in the upper right. But I know that on the left, what that is, that's a Nansen bottle. We named it after him because this is basically, and why did I do this? Anyway, a Nansen bottle is really cool because what you do is you drop it down in the ocean to a particular depth, and it's sealed. It's sealed up, and it drops down, say, to 2,000 meters, right? And then you drop something called a messenger down the line that it's connected to, usually a brass weight, and it falls and falls and falls, and it hits this trigger at the top of the Nansen bottle, and it makes the Nansen, the Nansen bottle's open when it descends down. Falls down to, or drops down to 1,000 meters. The messenger closes the valves, so you trap water at that depth. Isn't that neat? Sometimes they'll have dozens of Nansen bottles along a string, so they'll get a sample of many depths at the same time. So that stratification, that's where we get that information. So Nansen bottles, this could actually be a modified Nansen bottle that's used to measure current. So again, that's maybe why I put it up here. I don't remember, but they might, if I remember correctly, perhaps I put that up there because Nansen bottles are now fitted to tell current speed, so you can drop them down and get current speed at different depths. So, okay, what do I mean by current speed? All right. When the wind blows over the ocean, now this is intermediate, right? So in the northern hemisphere, the wind is blowing, towards the north in the northern hemisphere. So one towards the south, it always blows towards the poles no matter where it is. So anyway, so it's blowing along the northern hemisphere, and it's blowing straight across this patch of water down to a particular depth, about 100 meters. It's not real deep. The effect of this thing we call the Ekman transport, the transport part of that is the fact that something floating in the water, icebergs, ships, all that stuff, they actually move at a 45-degree angle off the wind. So you just let that thing float, and the wind is blowing at 0 degrees, due north. Icebergs and ships are going to be floating off to the right-hand side at about 45 degrees. Maybe Nansen was the guy that first noticed it. Anyway, so we're going to float. Now, actually, physics-wise, if you look at the brown arrows in that cube, the whole effect of the Ekman transport is there's a net movement of water 90 degrees from the wind. We only realize the 45 degrees for reasons that I'll talk about in just a second, okay? So when we look down at the 90 degrees is the movement if we take the entire column of water down to about 100 meters. If you want to, what do you mean column of water? Okay, well, water stratifies. It may not look like it's stratified to us, but in terms of the Ekman of transport, water causes an Ekman spiral, or the wind, causes an Ekman spiral. All right. Here's what I'm talking about. So here we are again. The water is blowing over the surface, or the air. The green arrows blowing over the surface of the water. Now, what that does is it causes the water to move off 45 degrees, right? And the reason why that does is because there's this balance that's occurring between the friction of the water and the Coriolis effect. In this particular case, it's the friction between the air and the water, so it's moving it off to the right, the Coriolis effect. It's spinning it to the right, about 45 degrees. It can't move it completely off to the right because, of course, there's the friction that occurs, and that takes away some of the energy. And again, it's only about 2% of the energy anyway. Now, that surface current of water, as it moves, rubs up against, all right, it actually causes a friction to occur with the water right below it. Now, the water right below it is a different layer because it's slightly cooler, all right? It might be slightly denser. Whatever it is, there's a layer between them. You can't necessarily see it. It's a climb, well, maybe not a climb, but it's a layering, just a minute layering at the very basic level. We're only down to 100 meters. So then you go in a little bit deeper. That layer of water is moving off to the right, and it's dragging the one with it. And of course, as you move down, the arrows are getting shorter because the amount of energy is decreasing because friction is sucking it up. Now, where'd the energy come from? It came from the wind. Okay? So you see why the arrows are getting small. That's why we call it Ekman spiral. So what we have basically is as we go down in depth, the water is continually spinning to the right. The Coriolis effect is causing that. And, of course, if the top water moves to the right, it's going to drag the water that's rubbing up against it, to the right. This is not like a gyro. We're going to spin in opposite direction for physics reasons, but it's going to drag that other layer of water to the right underneath it. So this one is coming to the right. Do it this way, Steve. This is coming to the right. It's going to drag the layer beneath it, but not quite as far because the layer beneath it has got more friction, less wind energy available to it. Eventually, theoretically, if you look at the very bottom, the little tiny orange arrow, that says that the water it can move in these directions all the way back in the opposite direction because of this Ekman. Spirals all the way down. Now, it only goes down to about 100 meters. That's the only effect because after that, there's not enough energy. The net movement of the Ekman transport then is that 90 degrees to the right, theoretically. Theoretically, 90 degrees, because of the ocean, because of nothing's absolute in the ocean, it's about 70 degrees actually. So the entire net movement is about 70 degrees. The guys that were noticing this were moving 45 degrees. We're only moving 45, if you're getting confused, why 90, 70, 45? Because they were at the surface. It's not so much the degree of the offset at that particular time, but the fact that they noticed that if they drifted, they always drifted to the right of the wind. All right? This guy, Valdred Ekman, he basically just quantified it for us. He says, all right, at the surface, you're going to blow 45 degrees off to the right, then the wind below it, it's going to blow a little bit further to the right, and at a little bit slower. So it's going to spiral like something that's spiraling and getting smaller as it's spiraling. Now, that's the physics. Why is that important? Well, you got to hold on for a second, because we're going to start talking about what happens when water, gets up to these boundaries, these western and eastern boundaries. So we're going to talk about western intensification. All right, we're going to talk about this idea that as the water is blowing, again, look at this map, from the right to the left, and it hits those boundaries on the left-hand side, on the west. That means you're going to have stronger currents. Western boundary currents are going to be intensified. They're going to be faster, right? They're going to be faster. They're going to be narrower. It's going to be a faster net movement of water. Maybe just a few degrees, but it is going to be faster, right? We're going to get this movement to the left-hand side, warmer water. So if we look at the topography here, and you look at the little white arrows across the Pacific, again, I'm talking about a net flow of air moving to the left. So in this particular case, we have 80 centimeters per second of wave movement. So that means there's a lot of water being pushed to the left, means a lot of waves going on there. The subtropical convergences that we're going to talk about are going to be those things that evolve when you get these waves start moving together. All right, so waves are going to move to, or water or currents, I'm sorry, are going to move to the west and intensify. Now, water moves in all kinds of different ways, and this is another, less dramatic, but still something that's got to be thought about because, less dramatic in terms of us sensing it. But this is going to be very important when we start putting together the fact, like I was talking about, the currents being moved to the left-hand side, to the western side of the Pacific. Again, we're going to be talking about El Nino. In the northern hemisphere, opposite in the southern hemisphere, what you basically get is, in this subtropical convergence, you get something called a geostrophic current. All right, geostrophic currents, geo is Earth, and trophic is dependent upon. Like we talk in biology about trophic levels, feeding, what you depend on to eat. So a geostrophic current is a current that's dependent upon the ocean, or dependent upon the Earth, excuse me. So what we have is, if you look at that picture at the top, in the northern hemisphere, again, opposite in the other one, you've got this idea that the water is moving to the right. You see the black arrows, they're spinning to the right. So the water, and that's the Coriolis effect that's doing that. So what that is doing is that's causing the water to move to the right. Now jump down to the picture on the bottom for just a second. And because of the way the Earth is spinning, that water is going to move to the right, but it's going to move faster on the left-hand side. That's western intensification that I'm talking about in a really grand level, just showing you in a small piece of water. All right, so basically what happens is the water is spinning to the right in those gyres that are throughout the ocean basin, but it's also bunched up on the right. That's the effect of the geostrophic current. The Coriolis effect is moving the water to the right. It's piling the water up in a bubble, and then gravity makes that bubble want to come back the other way. If you stop blowing on that cup of coffee, the water sloshes back the other way. All right. In a nutshell, what the subtropical convergence does or causes, this combined effect of the Coriolis moving the water and the water and the gravity moving the water the other way, and the effect is the fact that all of this is being moved to the left, moved to the west, is the entire ocean basins are sloshing back and forth. Right? As that water moves to the west, as it moves over there, like in the Pacific, over into Philippines and all those places I was showing you, it builds up on that side of the basin. And then these geostrophic currents, all these things add to that build up. And after a while, that build up's got to slosh back the other way. It's amazing to think But that's what's going on. These waves in the oceans are sloshing back and forth. But we'll talk more about that later on. Let's kind of make that connection now between all the physics and what that does to us. All right, these sea surface temperatures, these movements of water, have a very strong effect, not only just on the critters living in the ocean, but the critters living on land too. Remember, like I said, that's why it's warm at our beaches. That's going to affect where critters live. It's going to affect where all of these ecosystems that you see, in these maps. Now, this is, let's take a look and see which one. This has got to be, the top one is going to be winter in the northern hemisphere. No, excuse me, the top one's going to be summer in the northern hemisphere. And the bottom one is going to be winter in the northern hemisphere. And I know that because I'm looking at the North Pole, and I noticed that it's colder further south in the one in the bottom. So this is going to be our winter in the bottom, and our summer, us northern hemisphere folks, in the top. And this is how the temperatures change, and this is the stratification. That's what those little numbers mean. And again, they're showing you the currents, reminding you why the temperatures the way they are. Again, let me draw your attention here, because we'll talk about that more in the El Nino. Water's piling up on the left. It's doing it in the Atlantic too, but the Atlantic is smaller, so you don't get as much sloshing, right? So what kind of effect does this have? Well, for example, if you take a look at New York City, the latitude 40 degrees north, right? Latitude 40 degrees north, the average daily temperature in New York City in February is, the low is 2 degrees and the high is 36. That's got to be in Fahrenheit. I'm pretty sure I did that, because there's no way New York ever gets 36 degrees Celsius, which is about 97 in February, right? So this is going to be in Fahrenheit. So lows in New York City, 2 degrees, 36 degrees in February. Now, London, same time of the year, February, right? Same time of the year. Even further north, you would think colder, right? Nope. Lows are 70 and 45. Now, that's still cold as far as I'm concerned. But I can attest, when I went to London, even though it's much further north than Florida, that the weather, and I was lucky, the friend I was there said it was actually sort of unusual, but the weather was actually very pleasant and warm in London. Now, why is that? Well, if you take a look at the Atlantic Ocean for a second, you remember that the warm water is hitting us on the west side, spinning up to the right. Now, it's cooling off in the poles, but as it's cooling off, it's bringing a lot of warm air, which is bringing a lot of warm water up to England. See, England in that map is right about there. So the Gulf Stream warms England. All right. Now, that's why, if you live in the Pacific Northwest or up around San Francisco, that it can be cold even in the winter. I lived in Seattle for a while, even in the summertime. I remember a few Julys where we actually turned the heat on. It would be cold enough at night that you had to put the heat on, at least for me, because I don't like cold. All right. If you've ever been to Bermuda, you know that Bermuda is very tropical. Bermuda shorts, right? We think about tropical climates. We think about Caribbean. Some folks are surprised when you point out where Bermuda is. There it is in the map down below, the orange dot. It's right out there in the middle of the, kind of in the middle of the Atlantic. It's much north. It's latitude-wide. It's more like the Carolinas or Virginia, but it's very tropical. Average temperature in February in Bermuda is 18 degrees for a low, 64 for a high in February. It's not bad winter temperatures, but Bermuda lies right in the middle of that Gulf Stream, just being bathed by that warm water coming up from the Caribbean. That's why, I guess that's the good part, but when hurricanes form, they many times, because they'll follow the Gulf Stream currents, they follow those air mass moving in that direction, and of course the water moving in that direction, but sometimes as they make that corner and head north, Bermuda ends up being right in the sights. So there's good and bad, right, to living there. All right, now water moving across the surface causes upwelling, it causes downdwellings. Now here you see the green arrow, the southeast trade winds, or whatever wind is moving across the surface of the water is going to, and basically if you want to visualize this, as the water moves across the surface, it causes the water to peel, if you will. The water moves away from each other. So at the equator, for example, the southeast trade winds move the water away from each other, and that causes the water at the surface to diverge, to move off to the edges there, like you see in the picture in the upper right. And then, of course, it's a vacuum thing. Mother Nature Mother Nature replaces the water that moves away at the surface from water down below. We get an upwelling. Water moves up. Now, what upwellings do, all right, is they bring nutrients, they bring materials, and that's why we say they have a lot of productivity. Very high biological productivity in an upwelling. Biological productivity, a lot of things to eat, a lot of things eating things, a lot of biology going on there, right? Because in the cold water, nutrient rich. Now, nutrient rich because things that have died, decomposed, and other mineral reactions occur, things fall in the water, right? It's gravity. You're not immune to it in the water. Now, again, this divergence in circulating only occurs down to a certain depth because wind energy decreases as you go down to, so you got the Ekman transport going on, you got the currents moving, you got this, right? It's all very complex here. Now, the opposite happens when you get something called a downdwelling, like the vertical movement of water. So down in the lower left, the surface currents converge, winds can cause this, gravity, again, that whole geostrophic current that I talked about can cause the water to pile up. Remember, that's what the spinning does of the geostrophic current. As the Coriolis and effect and the gravity work against each other, the water piles up, and when it does, it gets heavier, it gets denser, and it falls. Topography, the bottom, what the bottom is like, what the kind of the sub, we're only down to 100 meters, so subsurface structures can cause this to occur too. So water's going up and water's going down. Now, another thing that can cause water to move in terms of gravity is density. So if the water increases in density at the surface, it'll fall because it's more dense. That's what we mean when we talk about density. It's basically how heavy something is in a volume, but just think about it as mass. As something increases in density, its mass per unit of volume decreases, so it's going to fall. All right, now put in the coast, and here's what you get: wind moving down the coastline. Okay. Whether we're talking, whatever direction it's moving, these pictures basically are the same thing, just the wind's coming from a different direction. So don't worry about that. But as the wind moves across, because of Ekman spiral, here's where we put that together, causes the water to move to the right. All right? As the wind moves across in the other direction, down below, the wind moves still to the right. Now, in the west coast of the northern hemisphere, if the wind, now this has to be set that because it's going to be different in the southern hemisphere and the other coast, but it's anyway, no matter where, as the wind moves down the coastline of anywhere, the water is going to move off to the right through the Ekman flow. All right, and as that does, it means the surface water is going to move to the right. The surface water is going to move offshore. You're going to get upwelling. So on the west coast, right, in areas in which the wind blows like this, and on the west coast of the United States, this is typically the way the wind blows. The wind can blow the other direction, but this is the net effect. And the west coast of the United States is known for being very productive. The western coast of South America, the wind blows basically the same way. It blows across in this direction, causes the water to move offshore, and that causes an upwelling to occur. Now, sometimes it works the other way. If the water's blowing the other way, then you can get a downdwelling. See, as the Ekman flow in the picture down below moves towards the coast, it hits the coast. Now it's got to go somewhere. The piles up and it sinks. We have lower productivity because the productivity is the stuff on the bottom. Mark Twain said the coldest winter I ever spent was a summer in San Francisco. And now when you think about what I've told you about the way the currents move, right? So the water, the wind usually moves down the coast from the north to the south, on the western side of the United States, and that brings that cold air from the poles down on top of us. So if you're living in San Francisco, on top of us, if you're living in San Francisco, that's why it can be very cold out there sometimes. So upwelling and downdwelling can be caused by just local offshore winds. Things underwater can change how the upwellings. The physics cause the way water moving around that sharp bend in the coastline actually causes the water to move away from that area of the upwelling, the surface water, so water comes up from below. Or if you don't have any sort of stratification, especially like if you don't have any density stratification, like in the high latitude oceans where there's a lot of water mixing. See, the high latitude oceans, remember, there's no Klein. So you don't get density, you don't get any density stratification. There's no waters moving past each other that could cause upwellings and downdwellings. Water's all mixed together. That's why, again, there's a lot of high productivity in those regions too, because you don't have to worry about an upwelling bringing the water. Areas of where it's cold, where there's no water mixing going on, means the nutrients are always mixed. So along the shorelines, especially in those areas, they're going to be pretty productive. So there's the Gulf Stream. I like that picture up above, the one that shows in color, because those are the pictures. You can see the eddies too, or gyres. Eddies are basically just big gyres, these warm and cold eddies. And what's cool about that is every once in a while, they'll find way up around Canada, they'll find some warm water tropical fish mixed in one of these warm water eddies. Now, if you look in the picture in the upper right, the eddies are green, which means they're cool, but not cold around them. They're certainly not yellow or blue like in the picture on the left. So they'll find something up there, and they'll say, oh, this is, obviously something that's been riding along with the eddies. Now, eddies form and disappear and move around like water swirls. So I guess if you're living in there, you're taking a chance. The Sargasso Sea. The Sargasso Sea is an interesting little detective story. And I always like to talk about science in terms of detective stories. You see what the Sargasso Sea is. Sargassum is that weed that we see that floats up on the beach a lot here in Florida. I'll show you a picture of it in just a second. But notice where the Sargasso Sea is. It's sort of the western end of this spinning current that's found in the Atlantic. Okay. All right, this is what sargassum is, the upper left. You see it oftentimes washed up on the beach. It's a good place for organisms to hang out, like that little sea turtle there that you see, especially when you're small. Now, Sargasso Sea is named because out there in the Sargasso Sea, out in the western end of the Atlantic, but still pretty far offshore, there's this huge mats of sargassum. So little baby sea turtles, when they're born on the beach and they scramble down to the water, they hope they can swim and make their way out to the sargassum, so they can hide and get bigger, so they can defend themselves. A lot of stuff going on in the sargassum, or out in the Sargasso Sea. Even though there's kind of in the middle of the ocean, this is an exception because it's like a mini floating ecosystem. There's no Sargasso Sea boundaries, right? So basically, this thing kind of moves around as this floating mass of productivities, floating mass of seaweeds float around. Another interesting thing about the Sargasso Sea is it was the part of a detective story between these two eels that you see. For years, we had well, not for years, we still do. We have American eels and European eels, and the only difference between them is the species name, if you know something about that. Anguilla rostrata, the other European eels, Anguilla anguilla. Basically very closely related to one another. And we always wondered, other completely different sides of the ocean, why these eels were so closely related. And we learned a little more about eel biology. Down below is a picture of an eel larvae. And eel larvae drift until they're turned into eels. And then at that time, these are freshwater eels. These eels end up swimming up into the rivers of the United States, America, or Europe. But when they're larvae, they're in the ocean. Eels are the opposite of salmon. These eels are anyway. They go to the ocean to spawn. Salmon go back to the river, These guys go to the ocean to spawn, and they spawned in the Sargasso Sea. And the reason why we figured that out, that little picture to the right, that shows the tracking of the larvae of these organisms. A little thing that leptocephalus is what it's called, that cool little thin thing on the left. It's weird to think that grows into an eel. Tarpon make the same thing, by the way. But what you see on the right is somebody tracking where those leptocephalus are found at different times of the year. So the gist of the story is the difference between American eels and European eels, why they're so similar, is they both breed in the same basic area, but American eels just develop faster than European eels, so they become eels faster than the European ones do, and when they do, they swim upriver, because as soon as they become an eel, it's time for them to get out of the ocean. European eels develop a little bit slower, so they end up over around Europe before they become swimming up the river. But they all go back to the same place. So then there was some debate a few years ago, but maybe there's no difference between them. I think they found that they pretty much, if they're mixing with each other when they get there, then there wouldn't be any species difference. Kind of neat. And of course, the loop currents, these are just basic little eddies. This is a good example, the ones in the Gulf of Mexico. This is why we get hurricanes doing what they do sometimes. Hurricane Charlie, for example, came this way through the Gulf and then went back through Florida that way, following the current. That's going to cause local conditions. Here's another really good example of local, but even bigger, monsoons. Monsoons are a massive amount of rain that occurs in the summertime in India and Bangladesh and those countries over there, where so many of the folks live in the lower lying areas, the areas basically up next to the ocean. So they get pounded by these monsoon rains, and not only they get pounded because they're at the wrong end of the wind. And what I mean by that, okay, in the wintertime, let's start with that first. In the wintertime, the wind moves from high to low in the red arrows, high concentrations to low concentrations. Think of wind flowing kind of downhill. Flows from high pressures to low pressures. That's what concentration is. Well, in the wintertime, you have lower pressure in the ocean, out over the ocean, higher pressure out over the land. Because in the wintertime, land cools faster than water. So that causes a difference. That causes a difference in pressure system. So the water or the air or the wind moves high to low, and we get the monsoon winds blowing offshore. All right, that's fine. Now, in the summertime, when the problem occurs, when these monsoons occur, everything goes the other way. Land warms up faster than the water. So as the Earth's tilt causes the northern hemisphere to face the sun and warm up, the land part of the northern hemisphere warms up faster. And that causes a low region, a lower pressure region to form, right? So we get a difference. It's not so much that, well, it is so much, but it's the difference because one of these is cooling off faster than the other. And the land, in this case, is warming up faster than the other. So the wind is going to blow from high to low. Monsoon winds bring currents, they bring rain, and they also push the water up against these low-lying regions. Right? And monsoons are seasonal, right? There's nothing you can do about that. It's because of the way the earth cools and warms as it moves through the seasons, as the sun hits the earth at different latitudes. This is pretty much a repeat, right? The Pacific Ocean, and now these currents break up into much smaller currents, the localized currents. You see the picture down below, but all together collectively they make the warm water currents, and then of course the cold water currents. Now the cold water current, you noticed in the northern Pacific, kind of moves along and breaks up into little gyres, where in the southern Pacific the cold water current doesn't have all these geological things to cause it to break up into these gyres as much. Localized effects at a global level. All right, El Nino, here we are. So I've set you up for this, talking about the wind blowing west across the equator. There is equator in the picture, and this is in the Pacific again. Water builds up a dome on the western side of the Pacific. The geostrophic currents cause this, the Coriolis effect, which causes the geostrophic currents, all this sort of stuff. It causes the water to move up on the left. Now, this is also caused because the prevailing, it is caused because the prevailing weather conditions, this thing called the Walker circulation. A Walker circulation cells, that's the green arrows. That's overall through the Pacific, the atmospheric conditions, the meteorological conditions, are going to cause the air to move in a clockwise direction, right, which is moving across the water. So I'm bringing two things together. Where air's moving this way, pushing the water this way. Going to get a lot more rain in the tropics there on the western side of the Pacific. You're going to get this westerly flow of water. Now the water builds up. Look at that picture in the upper right. That's again one of those things where the color, the red's color of the warm. That's what happens when too much water gets pushed up on the left. It sloshes, literally swoosh back to the eastern part of the Pacific. Can you imagine? Can you think about that? Think about a huge, massive amount of water. Look down below. You can see the warmer water is look at the darker, pink or red, orange. It's moving back to the right. Now, what that does is that hits the western coast of South America. It hits the western coast of the United States, too. But it was first known amongst the sardine fishermen on the western coast of South America because it seemed to arrive about Christmas time, El Nino, the Christmas celebration. But what arrived was this warmer water, and that will lower productivity because when warmer water is going to be denser, all right, because of the salinity. And when it hits the west coast, not only the density, right, there's a temperature and density, so it's going to kind of vary as it goes. But when it hits that west coast, it's going to curve downwards, and it's going to lower productivity because when in the picture up above, the water is coming upward, so it's upwelling. Upwelling's good. Downwellings are bad. Upwellings bring up nutrients. All right, so that's the El Nino. That's what we mean by the El Nino effect, and that's caused by the natural. Now, does it get worse if we cause these circulation cells to be stronger, if the winds to blow stronger through global climate change? Absolutely, that makes perfect sense, right? But these are natural things that occur, this sloshing. Now, the La Nina is actually the opposite. The La Nina is if there are unusual conditions that cause very strong winds to be blowing across the equator, right? And like you see in the picture there of the La Nina, you really got a lot building up on the west side. So think about La Nina conditions as normal conditions, but worse, but heavier, more intense. Right? And of course, now what La Nina brings is the opposite of the El Nino. The El Nino for the fishermen living on the West Coast, that was a bad thing. The anchovy fishermen, right? They were like, hey, where's all our anchovies? Well, anchovies feed upon smaller fish, which feed upon smaller fish, and eventually somebody feeds on the producers. The producers are the photosynthesizers, and they need nutrients to live as well as other species do. And in low productivity, there's not as many nutrients. Water's hitting that coast and going down. Well, nutrients are on the bottom. They settle down. It's gravity, folks. So look at the upwelling in the picture up above. Notice how the cold water is coming up on the eastern side up against South America. That's not coming up nearly as far during an El Nino, but during one of these, it's coming up much further. So La Ninas are good conditions for these folks, right? Now, of course, what's good for those folks on the West Coast may not be so good for those folks on of South America, but might not be so good for the folks that are on the western side. Remember the western intensification. All these things are going to be more intense on the western side of the ocean and more the Pacific because it's so big. There are cycles, more or less. I think they used to kind of go with 7 years, but now it was in the 20th century anyway. It's been anywhere between 2 and 20 years between El Ninos and La Ninas. El Ninos and La Ninas fluctuate back and forth. So the El Ninos are the red in the graph, the years across the bottom, and La Ninas are in the blue. So El Ninos are followed by La Ninas. And again, that's just kind of the balancing and the oscillation. Recently, they've come up with this idea of something called the Pacific Decadal Oscillation, 10 years or decades worth, right? Anyway, PDO, which, again, this is a long-term natural climate cycle. These winds changing in intensity during La Ninas and El Ninos and the sloshing that lasts an order of a few decades, 20 to 30 years. Now, again, don't get fooled when folks say about, well, these are natural cycles. Remember, nobody in global climate change is arguing that we're necessarily creating unnatural cycles, but we might be adding to them. We might be making these cycles more intense, more frequent, and that's going to change things. There's good or bad. That's going to change things. There's nothing you can do about that. That's just the way it is. What does the El Nino do for as far as we're concerned? There's another cool picture of during the La Nina. It's cooler on the western coast. During El Nino conditions, I was living out in California during one. The water was actually fairly warm, relatively speaking. But of course, that's good for us if we want to go on vacation. As I got for marine life, things are going to flood. Basically, I tell folks that what El Ninos do is shift around global climate patterns. Where it used to rain, now it doesn't rain. Where it rains. Where it used to rain a lot, or where it didn't rain, now it's starting to rain. Where the water was warm, now it's a little cooler. So things are melting when they shouldn't be melting, and things are cooler when they should be cooler. So you get impacts upon the coral reef. They're very sensitive changes in water temperature. Coral reefs don't do well with water temperature change at all. They're very, oh my God, and they die, unfortunately. Erosion levels change, storm patterns change, which cause erosion, droughts, and floods. Now, lots of time local things are causing these things, but in general, globally, what we see, El Nino ENSO is El Nino Southern Oscillation. Oscillation is the water sloshing back and forth, and the effect is, at least was first described in the southern Pacific Ocean, right? So it messes up the climates. Not only for us agriculturally or marine life, fisheries, but for organisms that live there. Now, since this is a natural part of the cycle, they've gotten used to these fluctuations, right? But again, global climate change, are we causing the fluctuations? And, you know, you can't say, well, they should evolve along, especially if you make the change things like overnight. It's kind of like saying that, well, the dinosaurs should have evolved. They were destroyed in one day, basically. The demise came in one day by an asteroid. Well, at least that's what we think. Now, way down at the deep ocean, we talked about most of this lecture about ocean currents, but what's down at the bottom of the ocean? Long circulation times, 4,000 years in some cases. Up near the polar regions, the high latitude, South or North Pole, the water starts to cool, obviously, right? And when it starts to cool, its temperature. Now, again, remember, temperature and density play this dance with each other about salinity, so about density. Sometimes, like in the terms of an El Nino, you get warmer water, and so you get warmer climate, you get more evaporation, you get greater density on the west coast, and the water starts to sink. Here the water's sinking, but it's not so much the density, or I'm sorry, it's not so much the salinity with evaporation concerns. It's more going to be the temperature takes over. So remember, the water in the polar regions is actually going to have a little less salinity because of the precipitation on the runoff. It's pretty doggone cold. So cold takes over and the colder water sinks. We know this, right? Diving in a pool again. So the cooler water is going to sink in those purple regions down to the bottom, and they're going to move. They're not going to be affected by the Coriolis effect or the Ekman transport. Again, those are only a few thousand years, that kind of thing. They're basically going to be affected by the underwater terrain, right? They're down the mountains underwater, and where this water falls down in those purple regions. But anyway, this deep ocean current, so this conveyor belt, is going to bring water around and around and around in these deep ocean currents. Now, the water is going to come back to the surface by basically just kind of warming up, if you will, as these deep, cold, salty water is moving to the ocean. It's warming up gradually, and the water is going to rise as it goes gradually. And many times, if it hits stuff underwater too. So if it hits objects underwater, it'll cause upwellings to occur, like up around the northeast coast of South America, if you see what I mean, right? Thousands of years. All right. Can we derive energy from the ocean? The ocean is an energy dynamic process. That's what's causing the water to move. It's wind and temperature differences, and things are moving. And the definition of energy in physics is the ability to do work. So things that move have the ability to do work. Your car moves; it has the ability to do work. You walk, has the ability to do work. Water moves; it has the ability to do work. Air moves. So we can use things like windmills. Spinning windmills in the wind. When the wind blows, the windmill spins and blah, blah, blah. We make electricity. Everybody understands that. Now, we can put windmills in the ocean, and that's actually a good thing because water, if you've ever experienced it, I'm sure, is much more dense than air, about 800 times more dense. So per unit of water moving through an area, there's a lot more force. If you've ever been hit by a 3-mile-an-hour wind, you probably didn't think anything about it. Nice light breeze. You hit by, say, a 4 or 3-mile-an-hour current, you feel it. There's more force there. Oh, okay. So we're going to be more efficient if we have these. You've seen the pictures down below, these underwater spinning things. They spin around and they generate electricity. For example, the Florida Gulf Stream current estimated to potential something like 2,000 megawatts, enough to give electricity over 1.5 million homes, right? Perfect. We should do that, shouldn't we? We should line the bottom of like the Florida Straits. That's what the picture's showing you on the white. The Florida Straits, the water moving through out of the Gulf Stream across between us and Cuba moves a lot, really fast through that area. It's being congested, right? Topographical regions cause changes, and of course the Gulf Stream is picking up and moving it. But we put a bunch of these down there at the bottom, or I don't know if we float them or whatever the case may be, we would have a lot of force spinning a lot of these propellers, making a lot of electricity. That's all very good. But here's a problem. Currents aren't always like the sun using solar power. Currents aren't always there. Sometimes they move a little bit. Sometimes they move just to, a few hundred yards or maybe a few miles, a few dozen miles. So do we plant the bottom with these spinning things? We do if we want to take advantage of the current doesn't go in the same place every time. It kind of does, weaves back and forth. Expense, they are expensive to maintain, but that cost will drive down as technology improves. they're underwater. So if you want to, you're gonna have to build big ones too, like the ones you see on land sometimes. And they talk about hazards to boating, even if you built them, deep enough. What about hazards to submarines? I guess they would have to know they're there. But what about all the marine life too? That's a problem. You think about organisms living in the ocean. Give them some credit for intelligence. Even if you go up to the marine mammals and such, they're not really used to living in an environment with these spinning big things going around, right? And the way these fan blades are designed is to spin, so they're sharp. So, and not to mention all of the other aspects of building the structures and maybe the noise. These spinning things may emit some type of a high frequency noise. And that's a problem for marine mammals. It's basically, they use that for communication. It's basically like for them, you and I trying to speak in a loud room. It's very difficult if there's background noises in the place. All right. So yeah, there are always goods and always bads. We have to find a solution to both. Maybe energy from the ocean. We have to do it in a sustainable way without affecting other organisms either. All right. Well, that's it for chapter 7 then. So.